Hi students, all of you welcome. Welcome to Suneel Engineering Academy. I am Sunil Kumar Bandar. Students, we have already completed 2 sessions in this basic electronics. This is the third one. If you want previous, click on playlist and you can find out the previous. Okay. Let us check up to which we have completed. All these are topic wise MCQs useful for both the electrical and also electronics engineering students. Okay, up to this one we have completed now. Coming to the first question in this session, in an intrinsic semiconductor is nothing but pure semiconductor. In pure semiconductor, no holes, number of holes is equal to number of electrons. Yes, it is correct one now. And electrons in the material are more than holes. There are no electrons in the material. So answer is option B. In pure semiconductor, always number of electrons is equal to number of holes, or concentration of electrons is equal to concentration of holes. We have already discussed in the previous session. Okay. The depletion region of PN junction, there are dash. Coming to the depletion region of the PN junction, what is this depletion region? Whenever the junction is forming by, here one side is doped with P type, one side is doped with N type. Here what is happening? Some of the positive will comes here, some of this negative will comes here. Okay, so it may be having immobile positive and negative ions. Immobile positive and negative ions. So these are immobile. So that's why this depletion region may not allow the electricity through this one like a conductors. Okay, so because of these immobile and positive and negative ions, it formed a region. That region is called as depletion region. Coming to the next one, very important question guys, immobile, positive and negative ions. Resistivity of semiconductor depends upon dash. We know very well resistivity depends upon nature of material or type of material and also temperature. Okay, but not depend upon any physical quantities. Length, it may not depend. Cross section area, it may not depend. Volume, it may not depend. Okay, all these are physical quantities. Length, area, volume. Okay, it may not depend upon all these. Atomic nature of the semiconductor, that is type of material or nature of material. Okay, in pure silicon, major part of the drift current is due to free electrons because of dash. Why the major part is due to free electrons? We know free electrons can move faster than the holes. The mobility is higher. Mobility, already we have discussed in the previous. Mobility of electrons is greater than mobility of holes. Okay, so that's why the major part of the current is flowed due to electrons. So mobility of electrons is greater than the mobility of holes. Okay, mobility of electrons is greater than the holes. Okay, for example, if you can consider germanium, the mobility of electrons is in the order of 3800 centimeter square per volt second. If you can consider holes, that is just 1800 only. That is nothing but like a 2.1:1 ratio. That means almost 2 times, twice. Okay, electrons moves twice that of the holes. If you can consider silicon, 1300 order, and that is mobility of electrons. Mobility of holes is nothing but 500 order, I think. Okay, 500 order. That means you will get approximately 2.6:1 now. 2.6:1. So almost you can say 2 or more than 2. That's why most of the current is due to free electrons only. Coming to the next one, in the following which indicates mass action law. Very important one. Mass action law. The product of N into P is equal to constant. That constant is nothing but intrinsic concentration square. So NP is equal to Ni square. Very important relation. Sometimes in the problems they will give Ni, NRP, any one, and asking other quantity. Okay, so NP is equal to Ni square. Ni is nothing but intrinsic concentration. Okay, so we have the values for intrinsic concentration, that is 1.5 into 10 power 10 centimeter power minus 3 for in case of silicon. In case of germanium, it is 2.5 into 10 power 13 centimeter power minus 3. Okay, so for germanium 2.5 into 10 power 13, silicon 1.5 into 10 power 10. Okay, so in the PDF I have given all the differences between silicon and germanium. Try to download the PDF. Here answer is NP is equal to Ni square. Coming to the next question, a specimen of intrinsic germanium with the density of charge carriers of 2.5 into 10 power 13 centimeter cube is doped with one donor impurity atom such that there is one donor impurity atom for every 10 power 6 germanium atoms. The density of germanium atoms is 4.4 into 10 power 22 per centimeter cube. The whole density is dash. The whole density is dash. So they are asking P, they are asking. Okay, so we know NP is equal to Ni square. So what is the N they have given? N is nothing but coming to the density of germanium atoms for every 10 power 6. So that is 4.4 into 10 power 16 you will get. Okay, so from this P is equal to Ni square by N. Ni, this is the intrinsic concentration, 2.5 into 10 power 13 whole square by 4.4 into 10 power 16. This is 10 power 26. 10 power 16 comes to the numerator, minus 16. 26 minus 16, 10. Okay. So 2.5 by 4.4 into 10 power 10. 2.5 whole square means 6.25. 6.25 by 4.4 is nothing but 1 point something. 1 point something, we have only one option, 1.4 into 10 power 10 centimeter cube per centimeter cube. So the answer is option C. Okay, clear? So NP is equal to Ni square. They have given N already, and P we want to find out. P is equal to Ni square by N. Coming to the next question. In a P type silicon sample, the whole concentration, directly here whole concentration given 2.25 into 10 power 15 per cubic centimeter. If the intrinsic carrier concentration is 1.5 into 10 power 10, what is the electron configuration? So NP is equal to Ni square now. So we want electronic concentration. N is equal to Ni square by P. Ni square. Intrinsic concentration 1.5 into 10 power 10 whole square by P is nothing but 2.25 into 10 power 50. So 1.5 whole square means 2.25 10 power 20 by 2.25 into 10 power 50. Okay. So this one cancelled out. This one comes to the numerator, 10 power 5 now. 10 power 5 is answer option B. Okay, 10 power 5 is nothing but answer is option B. Coming to the next question, guys. In the following, which relation is correct based on electrical neutrality? Based on electrical neutrality. What is the electrical neutrality? Neutral. Whenever the positive charge is equal to negative charge, you can say that is a neutral. Whenever the positive charge per cubic centimeter per cubic volume is equal to negative charge per cubic volume. Okay, so positive charge in the sense, come on, positive charge, we are getting the positive charge in case of due to donor impurities, and also P, we are getting the positive charge, and negative charge due to acceptor impurities and electrons. So Nd plus P is equal to Na plus N. Okay. So the answer is option C. Okay. So positive charge we are getting due to donor, ions and holes. Negative charge we can get negative. If anyone accept one electron, it will becomes negative. Now, for example, fluorine is there. It attract one electron, it will becomes F minus. Okay, it will becomes F minus. So whenever anyone accept the electron, it will becomes negative charge. Okay, so acceptor plus acceptors and also electrons. Electrons are negative charge. So positive charge is equal to negative charge. Positive charge, donor ions are positive charge and also holes are positive charge. Acceptors and electrons are negative charge. So LHS is equal to RHS, that is positive charge is equal to negative charge. So hence that is electrically neutral. Okay. Coming to the next question. In the following, which is Einstein's relationship? Einstein relationship is nothing but the ratio of diffusion constant to mobility. dN by mu n is equal to dP by mu p is equal to thermal voltage Vt. Thermal voltage Vt. So dN by mu n is equal to dP by mu p is equal to Vt. Yes, correct. So the answer is option A. This is the Einstein relationship for this diffusion constant with ratio of mobility. In the following, which is correct expression for Fermi Dirac distribution function? F of E is equal to 1 by 1 plus E minus EF by KT. That is option A. 1 by 1 plus E minus EF by KT. Okay, so answer is option A. In pure semiconductor, electric current is due to dash. In pure semiconductor, electric current is due to, here number of electrons is equal to number of holes now. So due to both holes and also electrons. Due to both holes and also in reverse bias. The capacitance present in forward bias and also reverse bias. And reverse bias. Okay, so if you can consider a PN junction, one side is doped with P, one side is doped with N. Between that, a depletion layer forms. Okay, that means it is positively charged and negatively charged. So between the two charged plates, one dielectric is there, then capacitance is formed now. Whenever you apply the forward bias, what is happening? The depletion layer width decreases. That means C is equal to epsilon A by D. The distance between those is decreases. Then capacitance will be more. And in the same way, whenever in the reverse bias, what is happening? Depletion layer size will be increases. So capacitance will be decreases. Okay, so the capacitance present in reverse bias is considered as transition capacitance. Transition capacitance. You can also say that it is the CT. The capacitance which is present in the forward bias is nothing but diffusion capacitance or storage capacitance. Diffusion capacitance or storage capacitance. In the forward bias, the distance between those is less, so capacitance is more. Capacitance is more. Okay, here distance between those two is higher, the capacitance is less. Okay, the capacitance is less. So here you can say CD is double greater than the CT. This is a very important one, guys. Nearly 5,000 times. Nearly 5,000 times. Okay, and the CT depends upon the voltage, the reverse bias voltage. The reverse bias voltage whole power n, or if you also consider the new voltage V reverse bias plus Vk whole power N. Okay, so this N value is equal to 1 by 2 or 1 by 3. If you can consider wave vector diode is based upon this transition capacitance only. For that, N value is equal to 1 by 3. These are the very important questions in the two capacitances. Okay, so here the capacitance present in both forward bias and reverse bias. Forward bias, in case of forward bias, D for D, diffusion capacitance or storage capacitance. In reverse bias, that is transition capacitance is formed. Based upon this transition capacitance, the vector diode is works. Okay, so here reverse bias, transition capacitance, and the CD, that is diffusion capacitance, is very higher than the CD. Coming to the next one, a PN junction diode act as dash. We know PN junction diode amplifier. No, it can be act as rectifier. Yes, it can convert AC to DC. Okay, and it may be also insulator whenever it will be act in case of reverse bias, but they have not specified like that. So the best application is rectifier. So can give the answer as option B. Okay. Gold is often diffused in silicon PN junction devices to dash. Why gold is diffused? Gold is the metal and it has very high positive temperature coefficient of resistance. So that means as temperature increases, resistance also increases, then recombination rate, I mean conductivity decreases. So to reduce the recombination rate, we use the gold. Okay, coming to the next question. PN junction diode dynamic conductance is proportional to dash. We know the conductance. Conductance is equal to current by voltage. Correct? That is nothing but we can say current by voltage. Resistance is equal to voltage by current, in the sense conductance is equal to current by voltage. That means conductance is directly proportional to its current. Conductance is directly proportional to its current. Okay, so GM is directly proportional to the current. Okay, so answer is option C. AC resistance of forward bias PN junction diode operating at base voltage V and carrying I is dash. The AC resistance is equal to change in forward voltage by change in current. So the answer is option D. Change in voltage by change in current. Okay. And coming to the next one, the diffusion capacitance of PN junction diode. Diffusion capacitance of the PN junction diode. The CD is generally proportional to E power V by zeta VD. That is, it is exponentially increases with the forward bias voltage V. Exponentially increases with the forward bias voltage V. Coming to the next question. The depletion region of semiconductor PN junction diode has dash. Given depletion region contains immobile ions, immobile positive and negative ions on either side. So the answer is option B. Coming to the next question. Which of the following statement is correct under small signal operation? First of all, if you can consider AC resistance is equal to sum of bulk resistance plus junction resistance, guys. This bulk resistance is nothing but the forward voltage minus Vk by the forward current, and junction resistance is depends upon that is a fixed value of the voltage by the forward current in milliamps. For this is 25 for germanium. In case of silicon, that is 50 millivolt. Okay, that means here the voltage is constant. It does not depend upon any forward voltage. Okay, so just inversely proportional to forward current. So for small signal operation, as IF is small, for small signal operation, IF is small means RJ is more. So RJ dominates dominates bulk resistance. Then RAC is approximately equal to RJ only. So here it's junction resistance predominates. Junction resistance predominates for small signal operation. For large signal, if IF is large, in case of large signal operation, IF is more, RJ is less. RJ is very less than RB. Then RAC is almost equal to RB. Then bulk resistance predominates. Bulk resistance dominates. Okay, all of you clear? So always consider with respect to RJ. Why? Because here voltage is almost constant. Only it will be with respect to the field current. But here forward voltage is also there. So we consider this one. So junction resistance is predominates whenever small signal operation. Coming to the next question. Junction capacitance of PN junction depends on dash. Junction capacitance will be depends upon both applied voltage and also concentration, doping concentration. Okay, both applied voltage and also doping concentration. Why? Because I have already given the capacitance is equal to 1 by V plus Vk whole power n. This Vk depends upon doping concentration, Qn donor Wn by. So that means it depends upon doping concentration and also the applied voltage. Coming to the next question, what is the typical value of the rate of current in PN junction diode in the forward bias and that in the reverse bias? We know very well in the forward bias, the current flowing is generally in milliamps. In reverse bias, the current flowing is nothing but leakage current, that is nothing but in order of microamps or nanoamps. So the ratio they are asking milliamps to microamps 10 power minus 3 by 10 power minus 6, that is 10 power 3 order. So the ratio will be in 1000 times, that is 1000 order. So the answer is option D. Okay, answer is option D. Coming to the next question, guys. In the following, which diode is generally operated in breakdown region? Which diode is operated generally in breakdown region? That is Zener diode. Why? Because in the breakdown region, it can be act as the regulator. It can be act as the voltage regulator. Okay, so that's why it is generally operated in reverse bias breakdown region. Okay, reverse bias breakdown region. Coming to the next one, which is act as a voltage regulator. Just now we have discussed, that is Zener diode act as a voltage regulator. Okay, all these questions belongs to special diodes. These are also very important, guys. Zener breakdown occurs when the reverse voltage is dash. Here we have two types of the breakdowns. One is Zener breakdown and the second one is avalanche breakdown. Avalanche breakdown. Zener breakdown generally happens in case of heavily doped regions. This is happens in case of lightly doped. Very important points. Simply you can remember Zener diode is the heavily doped diode. So Zener breakdown occurs in case of heavily doped. Avalanche breakdown opposite, lightly doped. Okay, so whenever the doping is more, if you doped more, then what about the depletion region? Less na? Depletion region less. That is, you can say narrow. Okay, here lightly doped means wide depletion region. Wide depletion region. So whenever there is a narrow depletion region, the depletion region is narrow here, very less. Then what about the requirement of voltage to break that? A very less voltage is also enough. So whenever the voltage is less than 6 volt also, it can break the junction. Okay, so but here if it is a wide depletion region, then we have to apply more voltage. So it happens whenever the voltage is greater than 6 volt. Okay, so Zener breakdown occurs less than 6 volt. Avalanche breakdown occurs greater than 6 volt. Okay, it is due to Rupture of covalent bonds. It is due to collision of atoms. Whenever the voltage is high, then collision of atoms takes place. So due to that collision atoms, the junction will be breaks. Okay, the junction will be breaks. So once again, guys, a simple idea: GNR breakdown. GNR is nothing but heavily doped. So it may be occurs in case of heavily doped regions. Heavily doped, whenever the doping is higher, depletion layer size is less. Okay, so that is narrow depletion regions. So whenever the depletion region is narrow, a less voltage is also enough to break the junction. Okay, that is less than 6 volt GNR breakdown. And here avalanche breakdown more than 6 volt. Why? Because it is a wide depletion layer. To break that, we require a lot of voltage. Okay, coming to the next question. GNR breakdown occurs due to dash. Just now I have given GNR breakdown occurs due to break or rupture of covalent bonds. Break or rupture of covalent bonds. Collision of atoms, this is avalanche breakdown. GNR breakdown occurs mainly in dash depletion regions. Heavily doped na? Heavily doped. Heavily doped means narrow depletion. So narrow. So the answer is option B. Avalanche breakdown occurs due to dash. Due to collision of valence electrons. I have already given. And avalanche breakdown lightly doped case. Correct? Lightly doped. Lightly doped in the sense depletion region, wide depletion regions. I think all of you clear. So many students just by heart these questions na. So no, not required if we understand in a simple way. Okay. And coming to the next question. In the following, which is used to remove unwanted ripples? The device which is used to remove unwanted ripples, that is filter. That is nothing but filter. Okay, so here there is no filter is there, so we have to select none of the none of the okay. Okay students, we will discuss the remaining questions in the next session. Okay, so if you have not subscribed this channel, please click up subscribe button and also share the videos to all your friends. Okay, due to your encouragement only I can take more sessions. Okay, so all of you try to uh, support for more sessions. Okay, thank you guys.